an equation, what this is saying is that the rank function of the dual matroid equals this. So if you want the rank of x in the dual matroid, then it's x plus the rank of E minus x minus the rank of the matroid M. So let me rearrange this so it looks more like what we did. So the first thing that I did is that I flipped. So instead of having x, I have E minus x. So the first thing I did was rank of E minus x. The second thing that I did is that I added level x on each row. And the third thing that I did is I subtracted 1, and 1 is the rank of the matroid. And so this is the rank of the dual matroid in terms of the rank of the matroid. Okay. Is this a proof? Did I prove this to you guys? I haven't proved it, right? I haven't proved it. What I did prove in making this argument is I said, okay, well, I started with something that was a matroid. Because it was a matroid, it had a 0 at the bottom, it increased by 0, 1, and it was submodular. Okay? When I flip it, submodularity is kept. When I add this over here, I fix the increase by 0, 1, and when I subtract 1 to everything, I fix my third problem, so I do have a rank function. In other words, I have shown you that this thing right here is a rank function, but I haven't shown you that it's the rank function of the dual matroid. Okay. Proof exercise. I mean, I don't want to prove everything I say because then we'll never get to cover anything. But I mean, one way of doing it is you just see, okay, what's an independent set in this matroid? It's an independence. So I is independent, or B is independent in this matroid if and only if the rank of B is equal to the rank of the matroid, which is equal to B. Okay? And you can just plug into here and see that this is equivalent to E minus B being a basis of M. And you have to do this, but exercise. This is not difficult, but you can do this. I showed you the rank function, and you know how to get the basis from the rank function. So what you have to do is take this rank function, compute the basis, and see that they actually are the basis of the dual matrix. Okay. Now, the reason that I want to do this is that I showed you guys last time how to talk about deletion and contraction using these pictures. Okay. And it's good that now you know how to talk about duals in terms of these pictures. And the reason why that is important is that there's a very nice relationship between deletion and contraction. Now, last time we already saw a nice relationship between deletion and contraction, which is that they commute. We said you can delete first and then contract first and then delete. Do it in any order you want. But there's another very nice property, which is that deletion and contraction are dual operations. And that is the homework. So if you contract T and take duals, that is the same thing as deleting T from the dual. And if you delete T and take duals, that is the same thing as taking the dual and then contracting T. So in other words, deletion and contraction are dual operations. Proof homework. This is your homework for exercise maybe 1A, is that right? Four. Oh. Anyway, it's in homework 4. You have to do this, and it's going to be much easier now that I told you this.
So Oxley actually defines contraction like that.
Yeah, Oxley defines contraction in this way. Because it makes more sense to you guys if first I tell you what contraction is and then I show you that it has. Anyway, okay, so I define deletion and contraction, and maybe I should remind you, just write down the equations. So I defined deletion according to the definition that the rank function of the deletion is equal to the rank function of the matroid, except you restrict to sets inside E minus T, and the rank function of the contraction was the rank function of X union T minus this. These were the definitions. We said that what this is either taking a lower cube or taking an upper cube in your big hypercube over there. So what this does is that it gives you one description of deletion and contraction. But you've seen that in matroid theory, we're not happy with just one. We want to know everything about this matroid. So for example, one thing that we should be able to find out is what everything is about it, what the independent sets are, all of these things. Okay. So let me tell you, for example, what the independent sets are. So the independent sets of a deletion are just the independent sets that happen to live there. So in other words, let M be a matroid, and T be a subset. The independent sets in the deletion are just the independent sets that survive when you delete T. So they are the things in your matroid which were independent.
By the second independent axiom, this is the same as all the independent sets intersect E minus T.
Yeah, sure. Yeah, another way of saying this is you take any independent set, you intersect it with E minus T, and you get something in here. You take any independent set and you delete the things in T. Those are the independent sets. And for the contraction, it's a little bit more complicated. So what you have to do is pick a basis for T. And the independent sets in here are going to be the sets I such that I is independent when you add this basis to it. And there's something non-trivial here, which we're about to prove, that no matter which basis you picked here, you get the same set. Proof. Yeah.
What was the thing you said about the first one, about intersection?
I said is, well, first let me say it in two ways. So the first way that I said it is that these are the independent sets disjoint with T. These are the ones. And what Jameson said is that another way of defining this is taking all the independent sets and deleting T from them. You're going to get exactly the same thing.
Wait, so take each dependent set and take out all the elements from each one, type T in them, or S in
Exactly. So you take each independent set and you throw away the elements of T that happen to appear in there. The collection that you're going to get is...
That's what we're saying.
It's not what we're saying. It's not what we're saying, but it is the same.
Well, because then you get...
I mean,
You might get multiple copies of the same guy. Doesn't really say it's the same guy.
you should think about this because it's not meant to be obvious. But yeah, it is true that if you take all the independent sets and for each independent set you throw out the things that are in T, then the list of things that you're going to get is exactly the independent sets is joined with T. But I think this is an easier description. You just look at the independent sets that don't have things in T.
This is like, it's the same, isn't it, as the restriction to set E minus T?
This is exactly the restriction to E minus T. Actually, we've seen this matroid before. This is the restriction to E minus T. This is also the restriction. Maybe I should say that here. M delete T equals the restriction of M to the set E minus T. Okay. People like to talk about deletion and contraction because they're dual to each other, and they don't talk so much about restriction because it's the same thing as deletion. Restricting to E minus T is the same thing as deleting T. What are these guys? They are the guys that are independent when you add B's of T to them. Or another way of saying this is you take the independent sets that contain a basis of T, and then you delete that basis of T. So you take the independent sets like this one, that contain a basis of T, and then you get rid of B of that basis and you get your set. So these are the independent sets containing a basis of T minus that basis. When you remove that basis from them. So this is the saying this in words.
So then what you were saying before was that we can actually just do it with one basis?
And the non-trivial thing is that you can just pick the basis ahead of time and do it with a single basis. So you could pick any fixed basis of T and do that process, and you're going to get all this the same answer. The proof is easy. The proof is easier than understanding the statement. When is, let's say that, so take some set in E minus T. When is A independent in M delete T? Well, what you need for a guy to be independent is for the rank to be the same as the size, right? But the rank of a deletion is just the rank in M deleted T of A is just the rank in the matroid of A. So A is independent in the deletion if and only if A was independent in the matrix. And that proves the first one. When is A independent in the contraction? Well, what you need is that this expression right here should be the size of A. Right? But what is the rank in the matroid of T? Well, that's why I had to pick a basis for T. So the rank in the matroid of T is the size of this guy, piece of T. In other words, this is the size of B sub T plus A. And then the last thing that I want to say is that if we look at the rank in the matroid of A union T, it's the same thing as the rank in the matroid of A union the basis of T. Because this guy has a certain rank, and all the other things that you add in T are already spanned by B sub T, so they're not going to increase the rank. So these two guys have the same rank, and this is A union B sub T. So, in other words, A is independent in the contraction if and only if A union B sub T is independent in the matrix. So there's the proof. Okay. You might have hoped for a description that is a little bit simpler of this guy, and it just happens to be a little bit complicated. It happens to depend on this picking a basis for T. That's what it is. Okay. So this is the one that I'm going to prove to you, and then the point is you can do this for anything else, for circuits, for flats, for closure, and so oppositions, you can write descriptions like this for the circuits, and you shouldn't copy, well, maybe you should copy this and leave empty spaces, because I'm not going to write all of this. It's on the notes, so I'm just going to ask you to see it there. But the closures, the lattice of flats, and you could continue. The height planes, everything. Okay? And so you should look this up in the notes, because I'm going to put you to sleep if I write down all of this. The point is that these descriptions exist, and so whenever you're working with a restriction, with a deletion or a contraction, and if you're wondering what a closure is or what a circuit is or whatever it is, then you have this catalog of things that you can look up whenever you need it. How do you prove them? In exactly the same way as this. These are exercises that, fortunately, someone already did the hard work for us, and we can just... it's good if you guys want to practice with these definitions to prove these things, but you should always feel free to use them. Okay? Now, one thing that I want you to notice is also that we said that deleting a whole set is the same thing as deleting the elements one by one. And contracting a whole set is the same as contracting the elements one by one. And so a lot of the times when you write proofs, and sometimes what you want to do is just contract the elements one by one and use induction. And that's always simpler, because if T is a single element over here, so let me go over here. Maybe I'll even write this out, actually, because this is how you normally use it. If T is an element, then what is this guy? Well, I had written it here. It's just the bases that don't contain the independent sets that don't contain E. Independent sets not containing E. Okay. What is this guy? Well, what is a basis for E? E. Maybe if it's not a loop, but if E is not a loop, then the only basis for E is E itself. And so what you're looking at here is sets that when you add E to them, they're independent. In other words, the guys that you have are the independent sets containing E. And then for each one of them, you just delete E. You had a set containing E and you delete it. What if E is a loop? If E is a loop, then a basis for a loop is the empty set. So this is the empty set, and these two guys are identical. So if E is a loop, then actually they're the same matrix, deletion and contraction. And so when you see it this way, you see that actually deletion and contraction are very easy on independent sets if you're only deleting or contracting a single element. Deletion are the things containing E, contraction are the things, deletion are the sets not containing E, contraction, the sets containing E, and you just get rid of E. And this is how you normally want to use deletion and contraction. And to emphasize that, I'm even going to erase this and keep this one. Now let me address a question that who asked me? Maybe Kim asked me last time about whether these notions of deletion and contraction actually agree with deleting edges and contracting edges in a graph. In other words, what happens when you do these operations of deletion and contraction on a graphical matroid? So minors of graphical matroids. Well, the thing is that graphs have a notion of deletion and contraction. So if you start with a graph and an edge in the graph, then we have notions of graph deletion and graph contraction. And you saw them in the previous homework. Okay. See that I have a graph that looks like this, maybe. And let's say that this guy over here is my element E. Okay. And what is the deletion? You just delete E and keep everything else alone. You leave it intact. You just delete E. So this is the graph. This is the deletion. And we have a notion of contraction, which is that of contracting edges. What does it mean to contract an edge? What you're going to do is just squish it and identify the two ends. Okay. So these two guys get identified, and so that means that I'm going to get something that looks like this. And then you see, when these two vertices get identified, the edge between them becomes a loop. So I get another loop here. And then I had two guys here. So this vertex is connected to this one and to this one, but these got identified. And so those are going to become two different edges, like this. Okay. So contract edge E, identify its vertices. Okay. This is contraction. In homework 3, you showed that when you delete an edge of a planar graph, that's equivalent to contracting that edge in the dual planar graph. And fortunately, these notions agree with our notions that we have defined here. So proposition is that taking, when you say graph minors are matroid minors. In other words, if you apply these operations on the graph, it's the same thing as applying them on the matroid. So if you take your graph and delete edge E, it would have been the same thing as if you deleted E from the matroid. In other words, the matroid of deleting the edge in the graph is the matroid obtained by deleting the edge from the matroid. And the other way around, the matroid of contracting edge E in the graph is the same thing as contracting the element E of the matroid. Okay? So let's prove that. Proof. So let's take, we have to show that something is independent here in this matroid if and only if it's independent in this matroid. So when is a set I independent in, no, let's do deletion first. Okay. Maybe the first thing I'll say is that the ground set of these matroids is the set of edges minus my edge little e. So the ground set is e minus e. So let me take a subset of the ground set and let's see when it's independent. Okay. Well, we saw that this set is independent in the deletion of the matroid, if and only if it's independent in the matroid. E is independent in matroid G, because those were the independent sets here. What does this mean? It means that I has no cycles in G. Saying that a set of edges has no cycles in G is equivalent to saying that it has no cycles, I should say circuits. In G minus E. Why is this? Well, it's clear that if I has no circuits in G, in the graph G, then it has no circuits in the deletion. This has even fewer edges. Why is the opposite true? Why is it true that if I have no circuits in G, deleted the edge E, then it has no circuits in G? Well, the only edge that you added from G minus E to G is the edge E. And so the only trouble is that that edge would cause you a cycle. But my edge E is not in I. And so that can't happen. And so what I showed is that I is independent in the deletion matroid if and only if it has no circuits in the deletion graph. In other words, I is independent in the matroid of the deletion. Okay. Are you guys done copying this down? I'm just going to change the signs and the proof is going to be exactly the same. So maybe I'll make it in a different color so that you can see what I changed. In case you stop paying attention, so whatever is red is that I just put it. Okay? When is I independent in the contraction? Well, I is independent in the contraction if, when you add E to it, it's independent. So I union E is independent. This means I union E has no circuits in G. Okay. And what I'm going to claim is that this is equivalent to saying that I has no circuits in the contraction. I haven't explained why yet. But if I show that, then I'm done, because the things that have no circuits in the contraction are independencies of this guy. So the only argument that I need to make is this one. Well, do you see why this is true? I mean, the idea is this, that let's say that you have a circuit in I union E has a circuit in G if and only if it looks like this. E, then I have a circuit, and then I have other things. That's my sketch of I union E. What's going to happen when I contract this picture? When I contract E? These two guys are going to get identified, and I'm going to get my cycle. Everything else stays intact, except these two guys got identified. In other words, I have a cycle in the contraction. And this is a back and forth. If I had a cycle in the contraction, then when I uncontract, my E is going to form the cycle that I'm looking for. So that's it. End of proof. Okay. And this is good news. This is very good news. So these graph operations that we have of deletion and contraction are generalized by the matroid operations. So there's no source of confusion here. And there's a corollary that is very important, which is this one. If you start with a graphical matroid, and you delete things, contract things, delete things, contract things, you do whatever to it, you take any minor of it, then you might as well be doing that to the graph. So any minor of a graphical matroid is graphical. So let me say that again. Consider any graphical matroid and any minor of it. Okay? If you have a graphical matroid, that means that it comes from a graph. Now you're taking minors on the matroid, which means you're deleting things, contracting things. But we just showed that deleting things and contracting things on the matroid is the same thing as deleting things and contracting things on the graph. And so in the end, this minor over here is represented by the graph that you obtain by doing these deletions and contractions. Any minor of a graphical matroid is graphical, and this is a very nice property. We'll see why this is super useful. It's a good thing. Okay. The next thing you might ask yourself is, okay, what about, so graphical matrices behave nicely with respect to these operations. What about these other families that we care about? For example, linear matrices. Okay. Do those behave nicely? In other words, do we have operations of deletion and contraction for vector configurations? So let E be a vector configuration in a vector space V, and let E be one of the vectors. I'm going to show you how to do deletion and contraction. So vector deletion, I need to produce a configuration of vectors for you. And the only natural thing to do is to take your collection of vectors and delete the one you care about. E minus E. This is the vector configuration in the same vector space. So deletion is easy enough. What about contraction? How do you contract with respect to a vector? What you're going to have to do is you're exactly going to do that. So if you know what this means, what you're going to do is take these vectors, but instead of considering them in V, you're going to consider them in V mod E. Now, what does this mean? Let me spell this out. These are the best ways in the picture. And so I'll just use the same picture that I use every time. Vector 1, vector 2, vector 3, vector 4, vector 5, and vector 6. Okay. So let's say that I'm going to first delete 5 and then contract 5. So to delete 5, you just consider all the same vectors. Except you forget that 5 exists. To contract, what you're going to do is this. You're going to consider so here's my vector 5 right here. Okay. Now, what you're going to do is look at the orthogonal complement of this guy. In other words, look at the hyperplane that's perpendicular to this guy. In this case, it's going to be something like this, right? And the idea is that this guy is the hyperplane perpendicular to this vector. And what you're going to do is you're just going to project all those vectors onto the hyperplane. Okay. So now, the configuration that I get for the contraction is, well, let's see, vector 1 stays where it is. 1, and so does 6. 6 is just sitting there. 6 stays there. 5 disappears. Now, for example, vector 2 is just going to land flat on this line. Right? So vector 2 lands over here. Vector 3 also lands flat on this line. Over here. And I'm missing vector 4. And what happens to vector 4? Vector 4 lands on the origin. So it's sitting next to 6. And this right here is my contraction. Chris?
We contract an element that's parallel to another element, and the other element becomes a loop after both of these cases, right?
Exactly. So if you contract 5, then because 4 was parallel to it, it became a loop. And you can also see that in that picture. When I contracted the red edge E, then the guy that was parallel to it became a loop. This is no coincidence. It always happens. So vector contraction, what you're going to do is consider the projection from the vector space to the hyperplane orthogonal to E. orthogonal complement of, I can't really say that it's the orthogonal complement of E because E is a vector. Orthogonal complements are of subspaces, and so really, this is of the span of E. And this should tell you something, that if E happens to be a loop, in other words, if E happens to be the zero vector, what happens? Well, you're taking the orthogonal complement of 0, which is the whole space, and so this is the projection of the vector space onto itself. It doesn't do anything, and so you just get the same thing.
What about this word? That's what matrix word, right?
So give me just a second. So what is the vector configuration if you're just going to do what I did here? This is E perpendicular. The projection maps this way. So this is the projection. You're going to take all of the vectors in E minus E and project them. When you are done, what vector space does this configuration live in? This configuration lives in a vector space of dimension 1 lower, in E perp. Okay. This is how you do vector contraction. What was your question?
The word minor. That's the only time I've ever seen that word before. Matrix minors.
I see.
I can't see the direct relationship.
So what is a minor in terms of these definitions? So you take a vector configuration, you delete some things, and you contract some things. And that would be what you might call a minor from the linear algebra point of view. The reason that definition doesn't exist is really because, as we're going to see, and of course you can imagine this by now, that these operations are exactly matroid, deletion, and contraction. And so proposition, and again I'm going to pull the same trick as last time, vector configuration minors are matroid minors. In other words, if I just take these guys and put these, I get a theorem for E of vector configuration. Okay. And I also get a theorem that any minor of a linear matroid is linear, which is a very good thing. Linear matrices also behave very nicely with respect to taking minors. So we'll start next time by proving this theorem, but I mean I almost wish I could prove it right now because all I would have to do is just delete G's and put E's. I mean the proof is the same. Okay? And actually you should think about it. Try to prove this yourselves, but the point is that this notion of taking minors in a matroid is a very good one because it behaves very nicely with graphs, and it does this natural operation on graphs, just deleting and contracting edges. And it behaves very nicely on vector configuration. It does the things that we do normally in linear algebra, which is either ignore some vectors or mod out by subspaces. All right. Go to the talk today. It's going to be good.
Test today.
Oh yeah?
Yep.
It's supposed to be early then.
Huh? I know. They're probably still standing outside waiting for you to come out because they're scared to come in here when you're asleep. Like, everyone's gone.
They're only taking cross products.
I know, you make them feel like they should know everything on this test, and then they get it. They're like,
Did I leave anything over there?
yeah. Look at that. That's you, isn't it?
Yeah. People should throw the ones that don't work.
Are you busy later? Do you want to get coffee?
Getting coffee with the speaker. You
Oh,
want to
the
join us?
speaker.
Join us too.
Is it just you and the speaker? Or is it
No.
everyone?
Gubelaza told me he's coming.
Okay.
Be around.
Okay, I'll see you later.
Hey, you're actually going to be on video for like 10 minutes. The stuff. So, don't do anything too funny.
Okay, turn it off.
I mean, I turned off the camera so you can do funny things away from the camera.
You're just not letting it go. Does everyone have blue books?
How's it going? You can do some study now?
Highly minimal.
Your wife said you were here till about 10 p.m. Some other chicks or
You know,
after the wife goes home.
yeah, I gotta stay late. Very necessities, gentlemen. I got David drinking coffee out
Okay, just take everything off of the table except for your blue book and your note card. No calculator. What's that? Same book as last time? Not if your old test is in there.
No, that's what he said. He's like reuse it.
Reuse it for like scrapping or not for your next
He's like,
test.
you can use it for your next one.
We got an extra one here. Never mind.
It's just slow.
Not for your
Does anyone else have extra ones?
I
I think he's walking down right there.
So if you old one, then just rip your old test out and put it away. I guess. You guys ready to start?
Yes. Start with.
Okay, tests are out, so no more talking.